There used to be this running joke in the science world. Fusion energy is always 30 years away. It was funny because, well, it was true. Every decade, researchers would get excited, make some progress, and then the goal line would just quietly move forward again. I stopped laughing at it recently because what's happening right now in a small city in northeastern Germany is genuinely not a joke anymore. In Greifswald, Germany, a machine called Wendelstein 7X has been doing things that weren't supposed to be possible this soon, and a startup that spun directly out of the research institute behind it just raised 130 million euros to turn this machine's legacy into the first commercial fusion power plant on Earth, with a grid connection targeted in 2030s. That's not a press release dream. That's a peer-reviewed roadmap backed by serious money and serious science. So let's talk about what's actually happening, why this approach is different, and why I think this might be the most important energy story of our lifetimes. The Wendelstein 7X, or W7X, sits at the Max Planck Institute for Plasma Physics in Greifswald. It is the world's largest fusion device of the stellarator type. The German government and the European Union have poured over 1.3 billion euros into it, and it first switched on in December 2015 with literally 1 milligram of helium gas. Now, before you glaze over the word stellarator, let me explain why it matters. Most people have heard of tokamaks, the donut-shaped reactors that dominate fusion headlines. The famous ITER project in France is a tokamak. Tokamaks work, but they have a critical weakness. They need a huge electrical current running through the plasma to stay stable. That current can suddenly collapse, which is something called a disruption, and this is a real problem for machines you want running continuously for decades. A stellarator solves that by design. Instead of plasma current, it uses a set of extremely complex twisted external magnets to confine the plasma. No current means no disruptions. The machine is inherently stable. The catch is that designing those magnets used to be nearly impossible because the math was too hard. Modern supercomputers changed that. Germany figured it out. The W7X is the proof. The device has 50 superconducting magnetic coils, each twisted into a shape that looks years of computation to perfect. When it finally turned on and the magnetic fields were confirmed accurate to within 1 part in 100,000, researchers from Princeton Plasma Physics Laboratory described it as a landmark moment. Every theory that stellarators could work at scale had just been validated in the real world. Now here's why it gets exciting. The W7X has not been sitting still. In 2023, it held a plasma for over 8 minutes, a world record for stellarators at the time. Then in May 2025, during the OP 2.3 experimental campaign, it shattered expectations again. On May 22nd, 2025, the W7X set a world record for plasma times of more than 30 seconds with a high fusion product, which is the technical way of saying the plasma was performing at power plant levels, and not just science experiment levels. The campaign pushed that further, achieving plasma durations between 30 and 40 seconds consistently. The machine also hit a total energy throughput of 1.8 gigajoules during a single 360-second run, surpassing its previous record of 1.3 gigajoules. The key metric here is the triple product, a combination of plasma density, temperature, and confinement time. During the 2025 campaign, W7X set a new world record for the triple product at long plasma durations, beating even tokamaks for sustained high-performance plasma. That is a massive deal. For continuous operation, which is exactly what a power plant needs, the stellarator design is now clearly in the lead. To be straight with you, the W7X does not produce electricity. It was never designed to. It's a research machine built to prove the physics work. And it has done that repeatedly and on record. Think of it like the Wright brothers' first plane. It didn't carry any passengers, but it proved flight was real. The W7X proves that a stellarator can hold a fusion-grade plasma continuously, which is one of the things that a power plant absolutely has to do. It is currently in maintenance phase and resumes experiments in late 2026 when the team will push forward towards a 30-minute continuous plasma operation. Now, only 3 years ago in 2023, a group of scientists from the Max Planck Institute did something that the institute had never done before. They spun off a private company. That company is Proxima Fusion, founded by the people who built their careers on the W7X. Former Max Planck scientists, MIT researchers, and engineers from Google X. Their goal is to take everything W7X proved and build a commercial power plant from it. In February 2025, they published a peer-reviewed paper in the journal Fusion Engineering and Design presenting their power plant concept, calling it Stellaris. It is described as the world's first integrated concept for a commercial fusion power plant designed to operate reliably and continuously. Not a proposal, not a concept sketch, a full peer-reviewed design accounting for physics, engineering, and maintenance from the ground up. In June 2025, they announced a €130 million Series A funding round, the largest private fusion investment in European history. Total funding crossed €185 million, and as recently as March 2026, the state of Bavaria committed an additional €400 million to back Proxima's work. Governments are treating this as a real national priority right now, not a science fair project, and they should do that. Their roadmap: in 2027, they complete their stellarator model coil demonstration magnet, proving high-temperature superconducting technology works at a scale for stellarators. In the early 2030s, their alpha demonstration stellarator achieves net energy production from fusion for the first time, and in late 2030s, Stellaris connects to the grid as a commercial power plant. CEO Francesco Sciortino said it plainly: the path to commercial fusion power plants is now open. Now, Stellaris uses high-temperature superconducting magnets that produce significantly stronger fields than older systems do, which means that the reactor can be much more compact. Smaller means faster construction, lower cost, and more flexibility in where you can build one. The design includes a neutron blanket adapted to the complex curved geometry of a stellarator. It captures energy from fusion neutrons and converts it to heat for turbines, and it breeds tritium fuel from lithium. The tritium breeding ratio is about 1, meaning that the reactor produces more fuel than it consumes. It is fuel self-sufficient. Because there's no plasma current, there are no disruptions, and you can actually design reliable support structures. The engineering team, including people from Tesla, SpaceX, and McLaren Formula One, have designed its support structures that can bear the full operational forces inside this twisted geometry. That is genuinely one of the hardest engineering problems in fusion, and they've addressed it head on. COO Lucio Milanese put it simply: design, not control, is our strategy. Stellarators are harder to design but easier to run. That is exactly the right trade-off for something that needs to operate for decades. Now, I've followed fusion news for years, and I'll tell you straight, this is the most credible commercial fusion story I've ever seen. Not because of the hype, but because the combination of factors at play here. W7X is not a concept. It exists, it runs, it sets world records. Proxima Fusion is not some random startup. It's staffed by the people who actually built and operated the W7X. Their design is peer-reviewed. Their funding is real and is growing. The timeline is ambitious but attached to concrete milestones you can actually track. Yes, Fusion has disappointed before. There are still serious challenges ahead, such as scaling from a demo reactor to a full commercial plant, managing tritium supply, building regulatory frameworks that barely exist yet for fusion. None of this is small, but for the first time, I look at a fusion roadmap and I don't see a vague future promise. I see 2027, 2031, late 2030s, all funded, all staffed by the people who knew exactly what they were working with and what they're working with now. If this lands, we're talking about energy that is carbon-free, produces no long-lived radioactive waste, cannot melt down, and runs on fuel derivable from seawater and lithium. There is no scenario where that makes things worse. It doesn't compete with solar or wind, it completes them. It's a baseload backbone that every clean energy grid on Earth is missing right now. The world has been waiting for this for 70 years, and for once, the people saying it's almost here are the same people who built the machine that proved it. That means something to me. 30 years away? Not this time, and I really mean that.